Okay, coming back to the hydrology session. Our next speaker is Chris Duffy from Penn State University.
Good morning, everyone. Took me a second to get loaded up there. I'm interested in talking about today the disparate kinds of domain data that might go into machine learning in solving some of the problems we have in hydrology and catchment problems. And I am part of the University of Minnesota-led KGML project. And I'll start off by telling you a little bit about my role. My role in this project is as domain scientist. I'm a modeler and a data analyst for hydrology for my career, and a collaborator with the University of Minnesota KGML science team in developing these new approaches to guiding physical understanding of hydrologic sciences. In this talk, we'll explore some essentially an ideal example where KGML might utilize co-located climatic, hydrologic, geologic, and ecosystem data and models, basically at an NSF-funded critical zone observatory that is linked to the historical climate reanalysis from NOAA and NASA. My work, just as an aside, my work environment uses e-notebooks, in particular Mathematica, for data analytics. And I make the comment because I believe the utility of notebooks for compiling, executing, and sharing the results of KGML is going to be important in the future for our colleagues to make advances as well. The overview, my objectives: develop a class of emulators that integrate global climate, land atmosphere data with high resolution experimental watershed data and models. My goal would be to apply KGML to advanced predictive understanding, building on current data models and state-of-the-art catchment information. Okay, a few questions. Won't be able to answer all these, but I think these are very relevant to the problems at hand. Can models and data from multiple physical domains, multiple resolutions and scales be effectively integrated in KGML? And from some of the talks we've heard today, that question may already have been answered. I don't know. What is the value of KGML in transferring trained nets to ungauged catchments? Still an issue, but again, there's some promising aspects of the earlier talks. Can we improve our biases and in particular uncertainties in the model? Once again, we're hearing that some of these things are well on their way. And one question I have for all of the presenters and maybe some attendees too: what are the essential data required for KGML? And how can we elicit sort of the community collaboration and the sharing and transfer of this knowledge? Okay, well, maybe I won't spend much time here, but hydrology and watershed science has a huge potential impact and is obviously related to the water balance changes as we have deforestation, urbanization, and climate change. Food security and supply is directly related to the hydrologic cycle on the land, as well as in the atmosphere, ecosystem services, floods, droughts, water supply, and then water quality. So modeling schemes. What are the opportunities for KGML in our project? And I make the point that all models should be made and implemented with a purpose. We have point models such as soil profile models or soil pack and snowmelt models, aggregate models such as SWOT that integrate over spatial dimensions and capture the aggregate effects. And then we have space-time distributed models that attempt to solve systems of PDEs for processes operating in the catchment. The interesting next step is sort of how do we link these kind of model information and their purposes and the data that goes with them into the, for example, network models, meta models, emulators, and I'll also bring in here reanalysis. Climate reanalysis is an important kind of data model structure that we make a lot of use of. And then finally, what are the products from this and how do we get them from data assimilation, prediction, and scenario development? Okay, well, I think network models, meta models, emulators, and reanalysis deserves a special look, and we'll, in terms of KGML, and we'll look at a little bit, an example of that. Land data assimilation systems from NASA and NOAA or climate reanalysis are used globally to get the atmospheric inputs to hydrologic systems. Climate reanalysis gives numerical representation of the historical climate. It assimilates past observations from weather stations and land surface data, satellite information, many other soils data, and even the vegetation and snowpack from satellites, for example. So it is a composite of not just numerical models, but all the collected data. What it's missing, in a way, is watershed and river basin data. And the other point I want to focus on in this talk is the role of experimental watersheds in making the connection. And that is co-location of instrumentation. Let's think of that as bedrock through boundary layer, where we have sites, experimental sites that measure all the variables in a co-located sense. Maybe another opportunity, and I'll try to make that case here. The Shale Hills Critical Zone Observatory in central Pennsylvania near the Penn State campus is the example I'll use. And it actually started as an experimental forest research station back in the 60s and 70s. So there is historical data as well. Then there's the Critical Zone Observatories are a national and even a global network of observatories where Earth system models are being instrumented and simulations models are implemented and developed on hydrology, water quality, geochemistry, geomorphology, etc. The Shale Hills experiment. This is only 8 hectares, and these are all sample sites. The little tiny dots are the ecologists went out and did biomass estimates and tree height measurements. It's a forested site, and they measured all the trees for their mass and height and other characteristics. There's weather stations here. However, it is an experiment. It's a short-term experiment. This part of the data was implemented from about 2008 through 2013 or 14. Or 15 maybe, and so there's groundwater data co-located with soil moisture profile data, as well as stream flow data, etc. So you get an idea that of the co-location as having a lot of variables to begin to test some of these tools. Here's gives you an idea of the geology. It's a shale under deeply dipping shales with regoliths where most of the water accumulates as groundwater. The models I'll talk about in a moment uses an unstructured grid. The upper left is a LiDAR image, 0.5 meter LiDAR over the watershed. The upper right is the soil type. The lower left is the soil depth, and the vegetation is figure 4. The PIM model is a distributed model that takes a system of PDEs, solves the PDEs and ODEs for vegetation, surface runoff in 2D, unsaturated flow and saturated flow over this unstructured grid using a finite volume semi-discrete approach. Okay, so what do we get? Well, what we did was run a data reanalysis for the later part of the record when we had the CZO data and did ensemble Kalman filter. That was Xiang Li in his work in WRR, and estimated the hydraulic properties of soils, with the data assimilation, and then other parameters as well. And then we ran a reanalysis from 79, in this case, to 2010, that gives us the precipitation, stream flow simulation. This is a reanalysis, of course, is a combination of data and model. And so in that sense, it's an ideal data set to begin to test some of these machine learning tools. Okay, so there's the groundwater signal, the soil moisture storage signal, recharge, and evapotranspiration components, canopy interception, blah, blah, blah. Okay. So what do we do with it? A product that everybody wanted to try, and this is Xiang Li's work, where we took that historical simulation record for this small catchment and mapped out a storm library where all the tropical storms and hurricanes that had an impact on the watershed, we pulled out. And you can see in the rainfall runoff curves in each of these, for each of the storms listed here. So this is just one kind of thing one can do. And there's a lot of reasons why a storm library like this could be valuable to studying things like climate change or land use change and that sort of thing. Okay, so the simple model of extending this strategy, here's just a elementary LSTM that we tried with 2 inputs, precipitation and evaporation. The idea here is to see whether or not the machine learning tools can learn from the historical data as well as the reanalysis data. And so here's a reanalysis training data set we used from 1979 to 99 that's showing rainfall and runoff at Shale Hills. And then here's the training experiment using the pre-CZO or pre-detailed observation experimental data, and simply using reanalysis and the hydrologic model as the 2 inputs and outputs. We then ran the neural net on those inputs and outputs, and you can see from the observed as the dots and the predicted, it looks pretty good. And however, when testing, we see, this is on the 2000 to 2013, we basically see a serious deterioration. So what you might take from this is just one of many examples that we're planning, but I wanted to point this one out because we're simply using the reanalysis to drive the model. And that's what most people tend to do when they use hydrologic models on a continental scale. And this is telling us, well, maybe that's not such a good idea. And we know that this later period has better data because we've been observing it for those many years. It's not model data anymore. It's really biased towards the real data. Okay, well, this is just a net train result that shows the quality of the training results, but we also should look at histograms of training and test simulations. The training data looks good. It captures the peaks, it captures the high values and the low values, where the testing data is really falling apart, and especially giving a lot of negative numbers here, which can be fixed easily enough, but it's still not going to get entirely get the data itself. Okay, so what are the next step in this process? We think this is a good experiments along these lines using assimilated data and models, and the physical model with reanalysis is an important product. I'm not trying to argue against that. What we need to do is to make this work at the small scale and scale it up to complex river basins. An example we're doing on another project as part of the DARPA World Modelers project is looking at really lightly gauged or ungauged basins in Ethiopia. This is a sub-basin of the Blue Nile in central Ethiopia. And the idea, of course, is we're going to have a lot less data. And there we've simply always have used reanalysis. So we've got to learn some things about what it is we can do in these sparse data settings, because in these areas, it's crucial to be able to do a better job of predictions. And we're always going to have limited data, at least on the ground. We have better prospects for satellites in the atmosphere and atmospheric information. Okay, so how do we go about that? Well, we've heard some ideas about this, but this is just some work of Ibrahim Damir and at Iowa. Basically, this is a nice article that talks about the hierarchical data model as a graph network. And we think this is a very nice way to begin to think about scaling up to the system. And we'll be doing something along those lines as well. As a matter of fact, there already are. My summary of this in this very brief and high level look at things is it is the ability of the machine learning to help us recover information from experimental data, very disparate kinds of data from experiments that have been done by earth scientists, hydrologists, and others, and integrating that into historical knowledge for KGML prediction. I think that could be a very important tool to recover some of this information into our modeling for future. Some values, rapid reconstruction of flood and drought response. I made a little case for that earlier. I'd like to know how good they are, and that would be a thing we could do. Ensembles of initial conditions for floods and droughts, we certainly need to think about how that can be done, and then to address uncertainty in weather and climate. Our challenges are manifold, but a few of them are just in extending and improving climate reanalysis with hydrological and ecosystem observation or in geomorphological observations. I noted that very little discussion was made about anything about the deeper than the soil profile in many of the talks. And I think the subsurface geology and the terrain geomorphology is an important element, I think, that there is data for. Design of machine learning tools for multi-domain data and models will have to be given some serious thought, I think. The river basin infrastructure management of municipal, industrial, agricultural, reservoirs, power systems, et cetera, is another huge challenge, and that's been discussed today. I think the Ethiopia example just makes the point, I think, of we need to think about providing international leadership for global water resources. And I thank you for your attention.
Thank you very much, Chris, for your presentation. There's just one comment that was posted. Maybe other questions will come, or questions will come later. But this question was that the person wants to point out a DOE experiment next year, which has very common themes for your Bedrock PBL. And the website, the link to the website for that is in Slido. So anybody interested in that can find that.
Oh, I think that's a very good idea. You know, in some sense, we're searching on a continental and a global scale for how this idea of integrating models, data, and machine learning will work. We can prove or disprove that only in a true experiment where most things are available and measured. And I think that's the point, the underlying point. It sounds like the DOE's got a good idea to advance on that front. So.
Yep. Okay, thank you very much, Chris.
You're welcome.
So our next, we'll get started on the next presentation, and that's going to be given by Ankush Khandelwal, and he's a graduate student in the Department of Computer Science at the University of Minnesota.
All right, I hope you can hear me.
We can.
Perfect. So hi, everyone. My name is Ankush, and I'm a researcher at University of Minnesota. And today I'm going to talk about our work on integrating physical principles into machine learning algorithms for hydrology. And this work is being done jointly by a number of researchers from both computer science as well as hydrology from University of Minnesota and Penn State University. Okay, so in the last few talks, we have heard a lot about streamflow and how important it is to estimate that or forecast that accurately. And there are a number of physical models that are being used to tackle this problem, but they face numerous challenges, and calibrating these models is one of the biggest challenges. And in a number of cases, we don't understand all the processes completely, which makes it challenging algorithms. And similarly, just using data alone might not solve our problem because it would require a lot amount of data to capture the complex relationships between our weather inputs and our output variables, which is streamflow in this case. And again, even if we have a lot of data, we might not get physically consistent results, which is also important in our application. Okay, so our goal basically is to see how can we bring these two things together, or the complementary aspects of these two aspects. Okay, so if we just quickly look at this problem from a machine learning perspective, a very reasonable thing to do would be to use a machine learning architecture which is time aware, and it takes weather inputs and then produces output variable, which is streamflow in our case. So very popular models would be using LSTMs or GRUs, and you have seen quite a bit of them in the past few talks. So this is just looking at this problem from a machine learning perspective. But if we look at this problem from a physics perspective, we can see that there's a very complex relationship between our weather inputs and streamflow. So here in this slide, I'm showing you a graphical view of the water cycle. And we can see there are a number of processes that are directly and indirectly related with streamflow. And another interesting property of our system is that it has a memory, which is basically the amount of water stored in the system at any given time. Basically that water could be stored in the soil as soil water or soil moisture, or it could be stored as snow. And the amount of this water has a big impact on how these different processes respond to our inputs. For example, for the same amount of rainfall, we can have very different surface runoff depending on how much water is already present in the soil. Similarly, on a very hot day, the amount of water that will become available by snow melt will depend on how much snow is already there on the ground. So knowing these storage variables can help us in doing a better job in estimating streamflow. So from a machine learning perspective, these two states are interesting. Okay, so basically our goal in this project right now is to evaluate the utility of incorporating these states and fluxes directly into the machine learning framework. Would they bring value? Would that reduce the complexity of our problem? That's what we're trying to explore in this project. So what are the different ways in which we can bring these states and fluxes into our machine learning? Again, the architecture on the left is the basic architecture that I showed before, that uses no physics information and directly tries to model streamflow from weather inputs. And the architecture in the middle is trying to show that we can bring in these extra variables as inputs to our system. For example, in the previous talk, Chris showed that he used precipitation together with evapotranspiration to drive his LSTM model. So this is one way in which we can do it, but in a lot of situations, we will not have access to these derived variables directly from reanalysis data sets. So a more general approach that we are exploring is to model these intermediate states and fluxes from our core weather variables, and then feed that to our final process, estimating streamflow. So for example, in this architecture, we are using weather inputs to first learn ET, soil, water, snowpack with different LSTMs, so that they can all capture different temporal scales and things like that. And then the output of these individual modules are fed to the final module, which is trying to estimate stream flow. So the benefit of this is that it reduces the complexity from one module to capture all of these complex processes together. And once we bring these things into these variables into the architecture, we can impose another layer of constraint, which is basically using physics-based loss functions to constrain these individual modules to adhere to our conservation of mass principles, and we heard about those in previous talks as well. So this is basically setting up the roadmap of what we are trying to evaluate or assess in this work. But in this talk, I'm going to just show a small set of results based on a very simple, relatively simple variation of this architecture, where we are not going to use physics-based loss right now, and then also we are going to model these individual states separately, and then pass that as input to our final module, which is trying to estimate stream flow. So in some sense, instead of learning them simultaneously, we're just learning them separately and seeing how adding these modules will impact our results. Again, and the reason why we focused only on soil, water, and snowpack is because these are the storage variables, and we wanted to understand their value in improving the performance. All right. So to drive all our evaluation, currently we are using a 200-year simulation that we generated from SWOT model, which is a hydrology model, and this was done for a watershed in southeast Minnesota. So basically, to drive the simulation, we need inputs, and so the inputs were created from a weather generator that is part of this SWOT module, and it basically creates these inputs, which is precipitation, temperature, basically min and max for that day, humidity, wind speed, and solar radiation. Again, this is a daily scale model, and I also want to highlight here that in all the few results that I'm going to show today are done on the simulation. We don't have results for real data right now, and we are working towards that. So when you create these inputs, you pass them to the SWOT model, physical model, and it generates stream flow and all the other different intermediate states and fluxes that it calculates. So our goal right now is to see how can we emulate SWOT effectively by bringing some of these physical concepts. So again, we're trying to emulate right now. We're not trying to do experiments on real world data. Okay, for a very quick overview of the experimental setting, we are going to use the first 120 years for training and last 80 years for testing. And we chose our sequence length for LSTM to be 180 days, which is roughly half a year. Again, we did a lot of optimization in the back. We tried a week, 1 month, 2 months, and 1 year, and things like that. And we picked half a year because it gave reasonable results. And then we decided the hidden features for LSTM to be 28 in our case. Again, so that's just the basic overview of the experimental setup. Okay, so now let's look at the results. So on this slide, we have calculated 2 different error metrics. One is RMSE that everybody's familiar with, and NSE, which is a very widely used metric in hydrology, which is trying to basically compare the estimates from a model, from a machine learning model, with a very baseline approach, which would be taking the mean of your observations as your potential model. So how better is a machine learning model than the baseline? So that's what NSE tries to capture. So now let's look at the results one by one. So the first row, it provides the, again, so we have two columns. One is for training RMSE for the first 120 years, and then test RMSE for the last 80 years. And the numbers in the bracket show you the standard deviation across 5 different random runs that we did for each of these scenarios. Okay, so the first row gives us the information when we just use physics, where we are not using any physics. So basically, start from weather input, have one LSTM that tries to capture stream flow. So we get an RMSE of 0.78. And then the second row gives the results when we added an intermediate module that tries to capture soil water. So basically, the goal of that module is to predict soil water at any given time, and then that becomes the input to our stream flow module. So as you can see that as soon as we add this module, the RMSE goes down to 0.56, and similar trend can be seen in the NSE value as well. So this kind of gives us a quantitative view of the utility of adding those intermediate states as part of the architecture. And then we added another module that tries to capture snowpack at any given time, and that further reduced the RMSE. So that kind of tells us that there is some value in bringing these concepts into the architecture itself. Now the time series on the bottom kind of shows you the result for one of the testing years. So here, the black diamonds that you can see are the stream flow from the SWOT simulation, because our goal right now is to emulate SWOT. So what we want is our machine learning algorithm to be as close as possible to these black diamonds. And the green circles are basically predictions from a no physics based model. And the red line is from a model that has both soil, water, and snow as intermediate states being modeled. So as you can see that the red line is much closer to black diamonds. If you look in the beginning of the year here, it's matching the peaks more accurately than not using those intermediate states. And you can also see that it removes the spurious low stream flow values from the predictions as well. So this kind of gives us both quantitative and visual validation that adding these states is bringing value to our machine learning architecture. All right, so now let's dig a little bit deeper into these storage variables, as I call them, to just highlight it for machine learning audience that there's very interesting patterns to these memories. For example, soil water, it doesn't start from 0 for any given sample. Like if you think from an NLP application, when you're trying to work with a sentence, in the beginning you have no memory, and as you see more and more of the sentence, you start building your memory. But in our case, if you take any 6-month period in this time series that I'm showing you, which is basically 10 years of soil water, you can see that it's not going to start from 0. So basically what we observed is that giving information about the initial state, value of soil water helps in modeling the soil water itself. Again, I'm not going into the details of how to do that, but that's one of the things that I want to highlight. So basically, we need to think of different ways in which we can model states rather than just using plain LSTM. And similarly, if we look at snowpack as a state variable, it resets after every season in almost all geographies. And then, within winter season, it could drastically drop down to 0 as well. So it has that property of accumulation and dissipation, but it happens at much faster than soil water. So very different temporal scales. But another thing to note about this storage variable is that it has very simple relationships with temperature. So we could reduce the complexity of modeling this variable by adding some of those physics-aware inputs or derived inputs. So these are some of the insights that we could bring in to model these storage variables. Now the final slide is about So what we did is we tried to compare our results from an LSTM with our physical variables to see if there is any physical meaning. So in this case, what we did is we just used our plain LSTM, which has a single module that takes inputs and produces stream flow. And then we compared the hidden features, like we have 28 possible hidden features, with some of the known quantities. In this case, you can see the top figure is comparing hidden feature number 23 with snowpack. And you can see that it has a reasonable agreement with snowpack, which is very interesting that even with no information about snowpack, a hidden feature is trying to emulate snowpack, which is a very promising sign from a machine learning perspective. And similarly, if you look at soil water, we see hidden feature number 4 shows a reasonable agreement with soil water. So here we are looking at 1 year's worth of data. So again, this just to kind of another way to validate that yes, these two states are important in doing a good job in estimating stream flow, and a basic LSTM is automatically trying to capture this. So our goal basically going forward is to come up with different ways in which we can model these states and memories by changing the architecture or bringing new ideas into the framework. So some of the other ideas that we are planning to pursue is so right now I told you that we individually trained LSTM for snowpack and soil water, and then fed the output of that input to the final module. But we could do that, we could train all of these simultaneously in a multitask learning framework. So we would explore that going forward. Again, we are going to add a mass balance equation to further constrain the model. And then the main important thing is to evaluate this strategy on real world data set as well. And finally, right now we are focused only on one watershed. Our goal is to analyze this across different watersheds, and we saw some very exciting data sets like camels, which would be a very good way to test some of these ideas. So that's all from my side. Thank you for your attention, and happy to take some questions.
Thank you, Ankush. We have right now just one question, and that is, how will you apply this framework on real data? I guess you will need observations on all state variables.
So yes, so the idea is basically use this as a pre-training mechanism. So in the previous talk, we heard about like transfer learning, where you learn a model in one setting and then you apply on the other. So you could do the similar strategy with using assimilation as a pre-training mechanism, and then you test it or fine-tune it on real-world data. So what we are going to do is, while we are pre-training, we will have access to those storage variables to learn those modules. But while testing or while using real data, we would be able to only fine-tune the stream flow module, but we could still apply the physics-based constraints on the other modules, which will indirectly impact our final result. So that's how it's going to play out with real world data.
We got some more questions. That's nice. Could you explain more about how you get the initial value of the soil moisture? Where can you learn?
Yes.
Yeah.
So basically, this was one of the ideas that we tried. Basically, what we did is, while training, we tried to simulate machine learning like a physical model that you would run. For example, when you start simulating from a physics-based model, you give it initial conditions like, okay, I'm starting it on day 1. This is the initial amount of soil water. It's already present in the soil. And then it simulates from there, right? So we kind of tried to do the same thing, where while training, we provided for example, we took the sequence length to be 180, which is half a year. So for any given sample, while training, we provided the soil water value on day 1 of that sample, and then just copied it for the rest of the sample. So basically what we are telling machine learning is that this is the value that's present today, now simulate soil water from here. So that's what we did, and we saw, so that the improvement that we saw from 0.78 to 0.56 was not happening if we don't add that concept. So that was during training, and then during testing, we just let the prediction of the previous sample served as the initial value for the next, and it worked fine. Again, that's just one of the ideas. There could be other ways in which we could bring that.
With that same question, there was a question about where they can learn more about this. Is there a paper or code? And I think that you'll probably say that there's a paper that will come out eventually, right?
Yes, it is. It will come out soon, yes.
Yeah, okay. Another one, since we do have time, what if the observed state variable observations do not obey conservation of mass? And I know that you haven't looked at the observed data in this analysis that you've been doing here, but I think that might be something you might project ahead to think about this.
Yeah, that's an interesting question. Again, as somebody asked that question previously, that you don't have observations of those intermediate state in real world. So we may not be able to even tell whether in real world it is being followed or not. We would just apply that constraint because we know by physics it should follow. So I think that's the best way I could answer that question, that what if it doesn't follow physics. Yeah.
Okay, and then one more question, that is, if the simulated soil water has large bias, and quote in parentheses, any validation of this, how would this affect your prediction of stream flow?
Yes. So we, yeah, I think what I'm trying to, what I'm understanding from the question is that a poor modeling of soil water can negatively impact our performance in modeling stream flow. It definitely can happen, but we haven't analyzed it that thoroughly yet. But what we saw was in our current experiment, if we use just 7 inputs without this initial value idea, we were not getting any improvement from 0.78. So that kind of gives you an indirect answer that a simple modeling of soil water was not enough to get that performance improvement.
Okay. Well, those are the questions we got. Thank you very much for the great presentation, and maybe there'll be more questions in the general question period.
Great.
So our last presentation is being given by Mike Friedel. He's from the Pacific Northwest Laboratory. Mike, there you go. You have to unmute yourself, Mike. There you go.
Okay, good morning and welcome to my presentation on the topic of a multiphysics-informed learning algorithm. Okay, is this a good start here? Good morning and welcome to my presentation on the topic of a multiphysics-informed learning algorithm for vadose zone transport modeling. This work was funded by the Laboratory Directed Research and Development Program at Pacific Northwest National Laboratory. So the outline of my talk comprises a background which includes a brief review of past and current studies, aim and objective, describing how this work differs from others, the algorithm which introduces 3 key components, and then some results comparing known to estimated parameters using the algorithm and comparing traditional to reduced order model simulations. So numerical vadose zone transport models require an inverse process to estimate parameters that cannot be explicitly represented. Combining the state measurements such as pressure head, temperature, and concentration in a multiphysics inversion is known to improve the property estimates given the presence of mutual information content. Some of the ongoing numerical modeling challenges that we come across include identifying influential parameters, identifying calibration data with mutual information, high performance computational resources necessary for multiphysics subsurface simulations. So machine learning solves three problem classes that include data-driven discoveries, data-driven solutions, and then combinations thereof. The data-driven solutions involve using unsupervised or supervised machine learning to classify, estimate, predict, forecast, or one or more response variables. For example, unsupervised learning was used to estimate continuous subsurface hydrogeophysical properties, whereas supervised learning was used to predict subsurface nitrate contamination, groundwater recharge, and groundwater redox status. There has been also some work done more recently using deep neural networks to predict groundwater recharge and forecast groundwater levels. And in the wake of these and other data-driven studies, there's a growing consensus that machine learning needs to respect the laws of physics. So physics-informed learning is an approach to combine the joint solution of numerical models whose, in this case, governing equations describe the physics of subsurface transport with machine and/or deep learning kernels. For example, my colleagues at PNNL recently implemented a multiphysics-informed deep neural network to jointly estimate the hydraulic conductivity, hydraulic head, and concentration values under steady state homogeneous conditions. The primary finding is that the physics-informed deep neural network is more accurate than the traditional deep learning neural network. Some challenges in implementing a deep neural network include things like they require a large number of hidden layers and a large number of training data. They're subject to something called the vanishing gradient problem, and they have trouble oftentimes generalizing to independent data. So in this study, the aim is to develop a multiphysics-informed learning algorithm for improved variably saturated zone parameter estimation and rapid reduced order transient modeling. The objective is to quantify and compare known estimated water, heat, and solute transport properties and simulated transient pressure, head, temperature, and concentration in a heterogeneous or layered variably saturated subsurface situation or zone. The multiphysics-informed learning algorithm proposed here comprises three primary components. In the upper left is a multiphysics numerical model. There's also surrogate machine learning models as a second component. And the third component is a multi-component objective function, of which I'll briefly describe these components next. The multiphysics numerical model used in the algorithm comprises a set of explicitly coupled partial differential equations that describe variably saturated water, heat, and solute transport. The joint inversion of these multiphysics model shows that mutual information in pressure, head, temperature, and concentration measurements improves property estimates. The figure at the bottom of this slide shows contributions of pressure head in blue, temperature in red, and concentration in yellow to property estimates, such as the hydraulic conductivity on the left and the heat capacity on the right. The surrogate machine learning models introduce a long-term field data to constrain the multiphysics-informed learning algorithm here. To test the algorithm, we conceptualized a managed aquifer recharge setting shown on the upper right. The correlated random variables are used to simulate stochastic boundary conditions that are applied to the numerical model, and resulting in stochastic subsurface pressure head, temperature, and concentration values shown at the middle panel. The bottom panel shows the complete data set, including time, distance, 12 properties, and 3 coupled state variables. Influential model parameters or features are identified based on mutual information content using learn heuristics algorithm. In this case, a series of neural networks with back propagation are evaluated using a genetic algorithm and a fitness function constrained by the 3 state variables: pressure, head, temperature, and concentration. To identify the robust features, we use random restarts of the algorithm and then evaluate the parameter modes. Important model features highlighted here in yellow with mutual information are the time, distance, hydraulic conductivity, thermal conductivity, bulk density, and dispersivity. In building the surrogate machine learning models, we use a random subset of the original set of models for training with subsequent random splits to independently test the trained models. This slide shows the results for an independent testing of a single coupled 3-response model with 6 predictors. Those are those property values. This unsupervised learning model results in simultaneous unbiased estimates of pressure head, temperature, and concentration that are sensitive to time, distance, and properties. In contrast to the unsupervised machine learning algorithm I just showed, none of the supervised machine learning algorithms, including the random forest, gradient boost and regression, ensemble, gradient boosting, and Gaussian processes, revealed sensitivity to subsurface properties. Given this finding, we train and test the supervised learning models to predict a single response as a function of time, distance, and the other 2 dependent variable responses. This figure shows training and testing of the supervised random forest machine learning model. The 4 panels in each quadrant indicate testing on the full training set and various random splits, including 20%, 1%, and 0.2%. The upper right quadrant reveals unbiased independent predictions of pressure head as a function of time, distance, temperature, and concentration. And similar unbiased results are shown across the splits when predicting temperature as a function of time, distance, pressure, and concentration, shown at the lower left. And when predicting concentration as a function of time, distance, pressure head, and temperature, shown on the lower right. The multi-component objective function is the 3rd part of the physics-informed learning algorithm. This illustration shows the minimization of differences between the measured and predicted pressure head, temperature, and solute concentrations when using the multiphysics numerical model as the first component and machine learning as a second component. Notice here in the second component that the random forest is used to predict the pressure head, whereas the ensemble gradient boosting is used to predict the temperature and concentration. Lastly, this multi-component objective function includes a smoothing constraint, a traditional Tikhonov regularization. Here we compare the parameter estimation layer results among the multi-physics joint inversion equations shown in green, in blue, in green, and the multi-physics informed learning in blue. There's 3 layers here, and the upper gravel layer is shown in the left panel. The middle silty layer is shown on the right panel, and a lower sand layer is in the bottom panel. In general, these results revealed that the multiphysics-informed learning algorithm had 1 order of magnitude less error than the multiphysics numerical inversion by itself. This figure reveals good correspondence between the results of the numerical multiphysics simulations of pressure, head, temperature, and concentration shown in the upper panel with the reduced order machine learning simulations in the lower panel. The reduced order model reflects training of the unsupervised machine learning algorithm using the physics-informed learning parameter estimates and stochastic boundary conditions. This reduced order model provides computationally inexpensive method to rapidly evaluate changes in boundary conditions on subsurface pressure, head, temperature, and concentration. In summary, the proposed multiphysics-informed learning algorithm reduced error in the estimated water heat and solute transport parameters by about 1 order of magnitude. And 2, it produced computationally inexpensive reduced order machine learning models for rapid pressure, temperature, and concentration simulations to inform management and policy decisions. So this brings me to the end, and if there are any questions, I'm happy to take those now.
Okay, thank you, Michael. I don't see any questions at this point, but they may still come up. So I'm just waiting for the questions to be sent to me that we're going to use during the general question period. That might take me a minute or two.
And since we have a minute,
Yeah, go ahead, Mike.
Yeah. I just wanted to point out that one large advantage in using this approach is that there's actually, this physics-informed learning algorithm reduced the computational burden associated with the traditional Jacobian matrix calculations by about 95%. So this reduced the number of iterations to convergence from 28 to 3. And using the reduced order model, what I envisioned in a larger scheme is the multimodal transfer learning and the application of this with geophysics to actually address that 3-dimensional estimate of continuous property values. And that some other people have mentioned about the scale dependence and issues. That's where this is going.
Okay, so I'm going to try to put together some questions. So I'm going to go through the list, starting with Gray. If everybody at this point, I think all the speakers can go ahead and show themselves, but just keep yourself mute if I am not asking you a particular question. So, so for Gray, let's see, I asked you one question, I think it was during right after your talk. So one question that came up was, there were a couple of other questions. So what data do you think is missing from the CAML data sets?
Yeah, that's a really hard question to answer. Keith's, can you hear me?
Yes.
Yep. Awesome. Yeah, Keith's response article hypothesized that it's geological data that's missing. I'm not 100% sure that that's true, and I honestly don't know how to answer the question. It's much easier to ask how much information is in data that you have than how much information is in data that you don't have. So I do want to say this. My presentation was very, very harsh, much more strongly worded than I actually believe. And one of the things that Keith said in his 87 paper and reiterated in his response to our paper that was the basis for what I just presented was that observational hydrology is the most important part of hydrological science, and I couldn't agree with him more. I think that let me just shirk the blame here or the responsibility here and say that the observational hydrologists, remote sensing, and in field studies, people that are doing things like operating the FluxNet towers, are doing the real work, the super important work. And so, because I don't have an answer to the question, let me just punt to other people that are better than me.
Yeah, if somebody else would like to respond to that one.
This is Chris Duffy. I think, in the end, it really depends what you want to predict and what are the variables. And it's not just stream flow. That's the point. I think that was kind of behind that question. And if you're mixing experiments like ecological ones with hydrological ones, and then things of water supply systems, they all have a different sort of needs, let's put it that way. And so I think the data required is going to be problem dependent. But I think at this early stage, it makes sense to find a few sites where you have all the data or co-located data that can provide the guidance to know how well you're doing. And if we're just curve fitting, I don't think that's enough.
Let me respond to that really quick, because I agree it depends on what you want to predict. But I also want to offer the perspective that we often know what we want to predict because we have actual societal outcomes that matter here. And one of the things that I am really trying to push back on is that there's some value, I'm not 100% convinced by this attitude that there's this value in much other than making the types of predictions that we actually need. So we can, we've seen a lot of presentations today, and we can do it in our lab too, and predict all kinds of different variables and the connections between those variables. But oftentimes the prediction tasks are pretty straightforward, and so there's a couple of perspectives we can take. One is, what can we learn from these things? And then that's the hard question, pulling out relationships from these models, although there are of course causal machine learning models and stuff. But the other one is just I think that one of the things that we should be aware of in the community when we're asking questions like this is that the data that we already do have contains a lot more information than we've ever been able to use before. And so all these are important, but that's really, I guess, to summarize the message I'm trying to give. Yeah.
I think that I believe it was Allison yesterday during the aquatic sciences session was talking about the societal relevance of machine learning, and I think that's what you're pointing to here, Gray. I mean, we might try to be able to predict all kinds of things using physically based models and so forth, a lot of details, but some of those things may not be. I think what you may be saying is that some of those things may not be immediately relevant. So to the being able to answer those societal questions, whether it's going to flood or not, those kinds of things maybe one needs to evaluate what we really need to know. And
yeah,
a second question for Gray is how might data from highly instrumented small experimental catchments help us to address the uniqueness of place problem that you talked about? Or do we need to look elsewhere?
So I do want to offer this sort of warning. Several of the LSTM papers that have been submitted to journals in the last couple of years try to use really small sample sets. So one of the lessons that I would like people to take from it, at least one of the things I've learned that I think is valuable, is that you're really not, it's not that you can't train models on a single site, it's that's not really representative of the full information content of the data. So if you have one really well instrumented site, that's all the data you have, you can do the best machine learning job you can to pull the information from that data. But if you were to live in a world with 1,000 really heavily instrumented sites, you would be pulling a different type of information from the data. You would be pulling a more generalized picture. And so I just want to caution that these really heavily instrumented watersheds can be interesting, but let's take seriously this lesson that the machine learning models are really learning a generalized representation. And so if we apply them to a single location or a single place, we might learn something about that place, but that doesn't really give us the full picture about what, it's giving us a very specific picture. So basically in the streamflow models, they're overfit if you train them to a single site, right? They do worse than if you train them to all the sites, right? And so I'm not saying you shouldn't use the data from the single sites. Just be aware that you're not getting the same structure of information in your models that you would get if you had data from a bunch of sites. And so there's that caveat behind any lesson that you could learn from that type of data set.
Okay, and I have a question that's not directed to anybody particular, but I would invite responses from anybody, and that is that the response of watersheds is unique to geographical location when it comes to ET, evaporation, soil evaporation, et cetera. How does machine learning address this variability? And since you're unmuted right now, Gray, or I think you are anyway, maybe you want to address that first, and because it might have been directed to you, but it doesn't indicate it from the question.
There's some degree of uniqueness of place in watersheds, but not as much as hydrologists think. So yeah, I mean, we're running some experiments now, information theory experiments, to try to quantify this, but I just want to also offer a warning. I mean, some of the responses we've gotten from this is that, that maybe we're not considering this uniqueness of place. And the only response that I have to that is that there is less unique, we know with 100% certainty that there's less uniqueness of place than the hydrology community has previously thought. There's more regularity in hydrological laws than hydrologists have, or behaviors across very diverse watersheds than hydrologists have previously been able to represent, at least in their models. So I'm not saying there's no such thing as uniqueness of place, but just be a little careful with that argument, because it's not as strong as it's sometimes made out to be.
Anybody else want to comment on that?
Well, I might just make a small comment that one of the things that we find that really helps a distributed model in, say, a river basin, which would be at a pretty large scale, is knowing the upstream phenomenon, what happened upstream. And it turns out that just a bit of more information on multi-gauges adds that information. And all of those gauges came from different parts of the catchment with different slopes. And they tend to have strong correlation with things like bedrock geology, with the slope, with the vegetation, the land use. In the end, I think people are going to want to know more than just the stream flow. And it's the collateral things that we also need to predict. And I'm not arguing that you can make a good prediction of stream flow in a regionalization like you're talking about, or even continental. I'm just saying that there's more to it. There's more things that need to be known and need to be predicted. I guess I'm not answering the question. I'm talking to Gray.
Yeah.
One of the cool things that we've discovered is that this is probably not a general, always true rule, but like if you have a water manager that's concerned with water quality, like dissolved oxygen content or temperature, you can kind of get some of that information. You can get pretty far addressing that problem, even though the data sets are limited by first training a runoff model. And then because there's so much of the sort of basic hydrologic structure, rainfall runoff structure in the model, then you can do something like real transfer learning, which means adding a new head layer to the previously trained model and just predict on the limited data sets that you have. And so it is possible to kind of expand these things too. And I just want to point out that that's one of the things that Alden does at Upstream, is he provides temperature forecasts and dissolved oxygen forecasts. And the strategy there is to first train a stream flow model and then train a new head layer to predict other variables.
There you go.
Yeah, I have another question that probably is for Gray, but I also have one for Xiaoping. So when you transferred knowledge to other regions, did you fine tune the whole model every time or just certain layers?
That'll depend on how much data you have. I think there's, yeah.
No, that was a question for, sorry, that was a question for Xiaoping. I'll get back to your question here in a second. Thank you, Gray. Xiaoping, did you hear the question? Is he still on? Yeah. So the question, Xiaoping, was when you transferred knowledge to other regions, did you fine tune the whole model every time or certain layers? So he must have stepped away, I guess. I'll ask the question that's here that I think is for Gray. There are very few USGS gauges in small watersheds. How can we understand or predict stream flow in small engaged systems that may behave quite differently?
Yeah, I think it's a good question. We haven't had that problem. The CAMELS data set includes basins that go down to 4 square kilometers, and we've not found a strong relationship between the quality of predictions and the size of basins, even in the out of sample tests. So, I mean, it's always a possibility. You're always going to find basins where this doesn't work. There's always going to be weird things that happen that you can't predict. And again, I just want to emphasize that we're definitely not saying that there's no such thing as unique basins. All I'm really saying is that there's a lot of information in the data we have. But we have looked at exactly at that using the basins we have, and our basins go down pretty small, 4 square kilometers, and we haven't seen any evidence of that being a problem yet.
Okay, thank you. Are there any other comments from any of the speakers? All right, so we're pretty close to the end here, just a couple minutes left. So I'm going to close the session now. Just remind everybody that this afternoon's session will start at 1:30. That session is about the atmospheric sciences applications of KGML. And also note that tomorrow afternoon, Thursday afternoon, there will be a session where we'll be essentially summarizing everything from all the workshops and also having a panel respond to questions. So thank you, everybody.
And John, I just have one little housekeeping item.
Yep.
If you are planning on joining us after lunch for the second session here, I just want to remind everyone to refresh their links if they're joining from the Zoom or YouTube links that they found on the website here. We will be updating those redirect links over the lunch hour. So please refresh these links if you'd like to attend the next session. The Slido link is exactly the same, so you do not have to refresh that one.
Thank you. And again, thank you very much to all the speakers. They all did an excellent job, and you made my job easy by staying on time. I appreciate it very much.